Logarithmic Differentiation, Part 3. Make sure you're familiar with your properties of logarithms, as well as the derivatives of logarithmic functions that we use frequently in this section. Now let's compare these two functions. So function 3 is y is equal to the natural log of a huge mass. And for 5, we have y is equal to a huge mass without a natural log. So if we look at 3, we're able to use log rules to simplify this. But if we look at 5, we don't have a natural log there, so we're not able to split this up, which means that we have to use quotient rule for the overall quotient and have to use product rule and chain rule inside. And that's a lot. So we kind of go, I really wish there were a natural log right here. And what's nice is there's actually a way to make that happen. The way to make that happen is to take the natural log of both sides. You just have to make sure that you're taking the natural log of both sides, not just one of the sides. So you have the natural log of y is equal to x cubed times arctangent of 3x times, all over inverse sine of x times the quantity x minus 2x squared to the 5th power. And now we're able to use log rules to simplify this piece. We just have to be really careful because we don't have just a y equals. We now have a natural log of y equals. So the natural log of y is equal to the 3 times the natural log of x plus the natural log of arctangent 3x minus the natural log of inverse sine of x, being very careful that we don't try to pull this exponent out because that's not actually an exponent, that's an indication that we have an inverse function, minus 5 natural log of x minus 2x squared. And now, it's not beautiful, but it looks much nicer. So we had that y was equal to this horribly gross function. We took the natural log and used properties to split it up so that we have a nicer function. It's not wonderful, but at least it doesn't have any product or quotient rule. Now we can take the derivative, but we have to be really careful because now y is inside of a function, so we have to take the derivative implicitly. The derivative of the natural log of y will be 1 over y, because the derivative of natural log is 1 over whatever's inside of it, times the derivative of what's inside of it, and the derivative of y with respect to x is dy dx. And that will be equal to, well, 3 times the derivative of natural log of x will give us 3 over x. Plus, now we have the derivative of the natural log of arctan of 3x, so that'll be 3 layers of chain rule, where outside of natural log, our next layer is arctan, and inside of that we have a 3x. The derivative of natural log is 1 over what's inside of it, so we have 1 over arctangent of 3x times the derivative of arctan 3x, so that will be 1 over whatever is inside of it, so 3x squared plus 1, times the derivative of what's inside of it, so times 3, so that'll end up being 3 over this 3x squared plus 1, minus, we have the derivative of natural log of inverse sine of x, so that'll give us 1 over inverse sine of x for that derivative of natural log of something, times the derivative of that something, the derivative of inverse sine of x is 1 over the square root of 1 minus x squared. Minus 5 times the derivative of natural log of x minus 2x squared will be 1 over that x minus 2x squared times the derivative of x minus 2x squared, which will be 1 minus 4x. But we don't want 1 over y dy dx. What we want is just dy dx. So we'll have to multiply both sides by y. So dy dx will be equal to this whole thing, which I'll simplify a bit. There's not too much simplifying that can happen, but a little bit of stacking. So that's 3 over x plus, well, this doesn't get too much nicer. I'll just change my brackets to parentheses. And 3x squared will give us 9x squared. And again, this next one doesn't get too much nicer. Just 1 over inverse sine of x. And then changing this to parentheses. So 1 over the square root of 1 minus x squared. At least this next one gets a little smaller. So we'll have 1 minus 5 times the quantity of 1 minus 4x. All over, I don't really need to, but I suppose I can factor out an x. So that'll be 1 minus 2x. And this, well, I multiply both sides by y, so I'll have this y over here. But I know what this y is in terms of x, and everything over here is just x's. So since I know what y is, I should substitute it back in. So dy dx will be equal to this whole thing again, so my 3 over x plus 1 over the arctangent of 3x times 3 over 9x squared plus 1 minus 1 over inverse sine of x times 1 over the square root of 1 minus x squared minus 5 times 1 minus 4x. I was trying to squish this, but I wrote it even wider. So minus 5 times 1 minus 4x over x times 1 minus 2x times y, and y is x cubed arctangent of 3x over inverse sine of x times x minus 2x squared to the 5th, which my spacing now is ridiculous, and I should have squished the other stuff a little more. So the trick here is just remembering this implicit differentiation when we take the derivative of natural log of y, multiplying both sides by y, and then substituting what y is equal to, since we know what it is from back at the beginning. So that general process is, if we have y is equal to f of x, and f of x is a gross function. And you might be like, what do you mean by gross function? So gross functions have lots of products, quotients, or as we'll see later, you have a function raised to the power of another function, as opposed to a function raised to a number or a constant raised to a function. And what we can do is take the natural log of both sides. So we have the natural log of y is equal to the natural log of our gross function. Just be careful, you take the natural log of both sides of our equation. And then we can use log rules to simplify this a bit. So this will be equal to some sort of nicer function. Where we use log rules to simplify. Or log properties to simplify. We call it all sorts of different things. And then we can take the derivative, and when we take the derivative implicitly, we end up with 1 over y dy dx is equal to the derivative of our nicer function. Where we'll probably have to use a bit of chain rule. But that's better than chain rule and a lot of product and quotient rule. Then we need to multiply both sides by y. Well, let me take derivative. Implicitly. Multiplying both sides by y, we end up with dy dx is equal to the derivative with respect to x of our nicer function times y, but we know what y is. Y is equal to our gross function f of x. So we multiply both sides, multiply. By y is equal to f of x, which is our gross function. And this is a lot, but usually it's a lot easier. You have like a smaller cognitive load than if you were trying to keep track of chain rule, quotient rule, and product rule all at the same time.